So our next speaker is Deepshikha Jaiswal Nagar. She's a professor at IISc Thiruvananthapuram, and she'll be telling us about quasi-1D antiferromagnetic spin chains.
Yeah. So thank you very much. I would like to thank the organizers for inviting me here and allowing me to present my work on these 1D chains. So this is work which has been going on for some time. So where we have discussed the Tomonaga-Luttinger liquid state and quantum criticality in this metal organic compound via something which is called as the Wilson's ratio, and I'm going to describe the details of this as we go along. So the plan of the talk is I give you an introduction to quantum phase transitions, Luttinger liquids, spin-off Heisenberg chains, and Wilson's ratio. Then we discuss the results and discussion, where I describe the thermodynamics in this copper-based metal organic compound, CuD, show you all these experiments from which we have calculated the spin-on velocity and Luttinger parameter for this system. This is the first calculation of a spin-on velocity and Luttinger parameter in any one-dimensional material. And then we have drawn a phase diagram based on the Wilson's ratio, where you will see some interesting features which are not predicted by theory. And we see quantum criticality extended over large portions of phase diagram, conclusions and future directions. Okay, so let me start with quantum phase transitions. As you know, these are t equal to 0 phase transition. So suppose you have a finite temperature phase transition, and you start to increase the value of the control parameter. So this transition temperature starts to depress, and at a critical value of this control parameter, this phase transition, which was happening at a finite temperature, starts to happen at t equal to 0, and this critical point is called as the quantum critical point, which separates these two phases, namely the quantum phase 1, quantum phase 2, and the effect of this critical point, which sits at t equal to 0, is felt in a large portion of phase diagram. This is what you see is a fan-like portion, which is called as the quantum critical region. Okay, so this critical parameter R could be anything varying from magnetic field, pressure, doping, etc. So the critical parameter R is called as the quantum critical point, and at this point correlation functions decay algebraically. Okay, so as I said, even though it sits at t equal to 0, you see the effect of this in a finite region, which is a quantum critical region. And the boundaries of these regions are given by this expression, R minus RC raised to nu z, where nu is the correlation length critical exponent and z is the dynamic critical exponent. So various theories predict different values of these parameters nu and z, and for a one-dimensional spin half, these have specific numbers. Okay, so now for systems with continuous symmetry and short range interactions and dimension d equal to 2, you know that because of Mermin-Wagner's theorem, there is no finite temperature phase transition. So the phase transition happens only at t equal to 0. However, if your system is a one-dimensional system, then there is no order even at t equal to 0. And such systems are described by Tomonaga-Luttinger liquids. Okay? So what I'm going to do now is introduce to you the concept of Tomonaga-Luttinger liquid before telling you about the realization of a Tomonaga-Luttinger liquid in an experimental system. Okay. So the hallmark of condensed matter system is this Fermi liquid theory, which describes interacting electrons in metallic solids. What I have drawn is a Fermi surface with a Fermi C. So in 2 dimensions and 3 dimensions, you have a very well-formed Fermi C and Fermi surface. What happens because of this is that low energy particle hole quasi-particle excitations happen very easily across the Fermi surface. But in 1 dimension, this Fermi surface reduces to just these 2 points here at plus minus kf. And the theory for this was constructed by these 2 gentlemen, Tomonaga and Luttinger, and they describe the interacting electrons in 1 dimension. Okay? So the Fermi surface, as I said, is just 2 points. So for 2 dimension and 3 dimension, what you have is a continuum of energies that will exist for all values of Q. For all values of Q, you have a continuum of energy here. This situation changes when you are in one dimension because the excitations can happen only across these 2 points. If you want to go away from these 2 points, you have to do a lot of energy cost. So therefore, there exists a forbidden region between this values of Q here where you do not have this continuum of energy. And these particle hole excitations in one dimension are bosonic in nature, and the theory for these was described by Tomonaga and Luttinger. Okay. So as I said, individual motion is possible in 2 dimension and 3 dimension because of the dimensionality which is present in the system. However, in 1 dimension, because of the lack of this dimensionality, such an individual motion is not possible. And therefore, what happens is that you have collective excitation similar to sound modes that you have in 3 dimension, which involves coherent modes of the entire system. And these excitations are what are called as spin-ons. So for instance, what I show here is this is a antiferromagnetic arrangement of spins on a lattice. And what happens on the bottom is that a spin on the second side gets flipped. Because of this, a quasi-particle which is called as spin-on is generated in one dimension. And in 1 dimension, as you see, as soon as you have a single flip, there are never a single spin-on which is generated. What you have is always a pair of spin-on which gets generated in 1 dimension. Okay. So density fluctuations, there are huge amount of fluctuations, quantum mechanical fluctuations in 1 dimension, and therefore this becomes the correct basis to describe the system. And the Hamiltonian for such a one dimension interacting system is represented by this. So what you see here is the Hamiltonian written in terms of these 2 parameters u, which is the velocity of the collective excitations. So this is the velocity of the spin-ons that gets generated in the system. K is a dimensionless parameter. It is called as a Luttinger parameter, and it denotes the strength of interactions. So to our knowledge, the calculation of u and k has never been done before in any one-dimensional system, precisely because of lack of experimental systems where you have such a realization of the theory. So theory also says that if k is less than 1, then the kind of interactions are repulsive in nature, whereas if k is greater than 1, then they are attractive interactions. Okay, so there are only these 2 parameters, namely the spin-on velocity u and the Luttinger parameter k, which is sufficient to describe the Tomonaga-Luttinger liquid. Okay, and the correlation functions, they found decays algebraically as -1 raised to r by r. This was done by Luther in 1978. Okay. So now let me come to a spin-half antiferromagnetic Heisenberg chain. What I show here is a cartoon of a one-dimensional chain. Blue spheres here represent atoms, and the red arrows that you see on top of them are spins which are antiferromagnetically coupled to each other. The Hamiltonian of a spin-half antiferromagnetic Heisenberg chain is given like that, where J is the exchange coupling constant, and SI denotes the spin operator on the IS site, and I+1 is the spin at the next nearest site. Okay, so this was solved exactly at t equal to 0 by Bethe. It is known by this very famous Bethe ansatz. It was extended to finite temperatures by Klumper, by a bunch of other people, primarily Klumper, by a combination of what is called as thermodynamic Bethe ansatz. So what he does is he treats this spin-ons with a velocity u, and they are related to the exchange coupling constant J by this expression u equal to pi of J. Okay, so what they find also is that spin-spin correlation functions decay algebraically at t equal to 0 in this fashion. So which means that just by the previous slide that I have shown, this system is also quantum critical at t equal to 0 k, and there are gapless spin-on excitations having a quasi-linear dispersion. Okay, so the first experimental realization of a spin-on spectrum like this was made on this material, potassium copper fluoride. In 2013, this is an inelastic neutron scattering experiment which is showing the energy versus wave dispersion. And as you see, as was predicted, The spin-ons are always created in a pair, and then there are these forbidden energy regions where you don't have enough spectral density, and then there are continuum at other positions. So, but case UF3 is not a very good realization of a of a one-dimensional Heisenberg chain, because at temperatures of the order of 100 or some Kelvin, there is a three-dimensional ordering happening in this system. Okay. So as I said, the ground state of a spin-half antiferromagnetic Heisenberg chain is a Tomonaga-Luttinger liquid. There is no magnetic long-range order at T equal to 0 Kelvin. Okay. So basically, if your control parameter R is something below a certain value, it's a Tomonaga-Luttinger liquid. And what was found by people is that in a Tomonaga-Luttinger liquid, this system, even though it is critical in the absence of any field, as soon as you apply a field and you keep increasing the value of field, what you have is a line of critical points which terminates at a saturation field, which is HS. So what happens in a Tomonaga-Luttinger liquid is that it is critical without any field. It is critical up to a saturation field, HS, beyond which the system transforms to a fully polarized state. And there is a scaling behavior associated with HS, which is given by these two lines. This is a theory prediction by He et al. In 2017. They say that very close to this critical point, the line is going to be linear. It's going to be of this form. So it goes linearly, the spin-on line goes linearly with the field by just this value of the slope, which is given by the exponent, by the number alpha 1. And similarly, on the other side, when you have a fully polarized state, the quantum critical line, which is given by Magnon, actually the Magnon word is not the correct one to describe the excitation of the fully polarized state, but anyways, that is again linear in field, and it is given by this expression here. So in between these two lines is a quantum critical region, and the calculations and predictions, etc., have been done very close to the saturation field HS. Okay. So this is the last part of my introduction, where I describe to you the Wilson's ratio. As you know, Wilson's ratio is a ratio of magnetic susceptibility chi prime to specific heat divided by temperature. That is a expression written on the left side for you. And for non-interacting fermions, Rw has the value 1. For very strongly interacting systems like Kondo lattice in spin half, in spin impurity, in single impurity limit, Rw has a value 2. So basically, Wilson's ratio is a measure of interaction effect and spin fluctuations in condensed matter systems. It is supposed to be much larger than 1 in strongly correlated systems where spin fluctuations are highly enhanced. Okay, so for a Tomonaga-Luttinger liquid, Guan and all predict that Rw should be equal to 4 times the Luttinger parameter K. So this is a phase diagram which was made by He et al. In 2017. So what you see on the y-axis is temperature, on the x-axis is magnetic field. 14 is the value of saturation field for a particular spin-half Heisenberg chain that they have considered. The contour plots are made with respect to the Wilson's ratio Rw. So you can see that the value of the Wilson's ratio is between 2 and 3.5 in the Tomonaga-Luttinger liquid phase here. It has a very large value ranging between 3.5 to 10 in the quantum critical range here, and then it falls down to 0 in the fully polarized region on the right side of the phase diagram. So till now, there has been no experimental verification of such a theoretical phase diagram as was made by He et al. And so what we have done in our experiment is to show you an experimental phase diagram which actually has the values of Wilson's ratio, which is matching with what is predicted by these gentlemen here. Okay. So the thermodynamics of a spin-half antiferromagnetic Heisenberg chain was first calculated by Klumper, as I said, in 1998. What you see on the left side is low temperature susceptibility. So these values of susceptibilities are for values of fields which are less than the saturation field. So you see that there is a peak here which starts to go towards the left as I keep increasing the value of the applied field. As soon as I reach the saturation field, you see that the susceptibility diverges here, and with further increase in field, it comes back, and what you have are peaks again on the other side. Okay. These are the plots of specific heat. What you see is a plot of specific heat as a function of temperature for different values of fields. And when you are in the Tomonaga-Luttinger liquid state, you see that there is a low temperature peak, which at low temperatures is actually the specific heat, So at low temperatures, you see that the specific heat varies linearly with temperature. Why? Because GMRC and all predict that it goes linearly with temperature, describing the fermionic excitation. The spin-ons are fermions in nature, and therefore, if that is the case, the specific heat should be going linearly with temperature. When you keep increasing the value of field, as soon as you go towards the saturation field, you find that there is an exponential drop in specific heat here, because now we have gone into the fully polarized state, which has a energy gap delta, and therefore the specific heat will go down exponentially in that case. Anyways, what I show you here is the first experiment which was done by Kono et al. In 2015. So what you see is that they have these same, these are measures of magnetization as a function of temperature for different values of applied fields. And you can see that as soon as they reach the saturation field, which is 14 Tesla in this case, there is a divergence, okay? The problem with this is that it was measured on this material which is called as copper pyrazine dinitrate. It has an exchange coupling constant of 10.6 Kelvin. So because of the large value of exchange coupling constant, the corresponding saturation field in this case is around 14 Tesla. So in lab magnets, using lab magnets, they are not able to go to values of, they are not able to go to values which are higher than the saturation field. So they go only till 16 Tesla. And similarly, Bruning et al., they have measured specific heat as a function of temperature and both as a function of field. The dotted line here are the theory calculations, and you find that the theory does not fit the experimental data very well. Okay? So what one needs is a good realization of a spin-half Heisenberg chain, which enables us to study the large portion of phase diagram and, if possible, to get as good an experimental realization of a spin-half Heisenberg chain. So therefore, what we need are moderate values of the exchange coupling constant J by Kb. And this was done in our lab using this metal organic compound. We call it CUD for some reasons. What it has is in the center, a metal center, which is copper here. It is bounded by oxalate rings. Again, on the right and left side, what you see are these pyridine rings, and then there are two water molecules. We were able to grow the single crystals of these large size single crystals by some technique which is called as layer diffusion technique. You can see that the crystals are approximately 5 millimeter in size. And from single crystal XRD, what you find is that these copper atoms form a chain in the A direction. The chains are very well insulated along the other two directions. The value of the difference between the copper sites on the other two directions is around 11 and 22 angstroms. So which means that this system is a very, very good realization. I mean, at least structurally, it has a very, very good isolated one-dimensional chains in the A direction. So if I make a cartoon of this, what you find is that the intra-chain coupling constant J in the A direction is of the order of 3 Kelvin. And because of large distances in the other two directions, J prime and J double prime are very, very small. But we still have to confirm the actual value of J prime and J double prime. So what we did was then, we did a susceptibility measurement as a function of temperature. What you see is a peak at around 1.2 Kelvin. This low dimensional peak is low temperature peak is an indicator of low dimensional magnetism. The red lines that you see on the black data are the theory fits. They are fits to Bonhoeffer model, which indicates that the ground state is a spin-half Heisenberg antiferromagnet. From the fit, we were able to get J by Kb as 1.23 Kelvin and the corresponding saturation field of around 1.75 Tesla. So you see that you have a very good and a very low value of saturation field, which makes it possible for us to probe the other side of the phase diagram very well. So this is a plot of magnetization as a function of field. Once again, blue is the measurement done at 0.38 Kelvin, and black is the theory, and you see that it fits quite well. So 2 Tesla indicates crossover to the fully polarized state. Okay. So then what we did was we did magnetization experiments as a function of temperature for different values of applied fields. So first thing that you see is a low temperature peak at some temperature Tm. As I keep increasing the value of field, you see that this peak keeps shifting towards the left, as is what is expected from theory. The black lines that you see, black lines, they are theory calculations. They are done by Bethe-Ansatz with only one fit parameter, J by Kb. The value of J by Kb that we gave from experiment as 1.23 Kelvin was given as a value for the theoreticians, and using that value of J, they have calculated these fits, and you can see that the fit is matching very, very well with the experimental data. More or less, it almost looks like a plot of data with line. So CUD is an extremely good realization of a spin-half antiferromagnetic Heisenberg chain. And as I said, these peak indicates crossover from Tomonaga-Luttinger liquid to quantum critical state. Now from theory, these are the predictions of the values of Tm that you should get with respect to the exchange coupling constant, with respect to all the values of mu b's and j's, and we have very, very good matching with respect to what is expected from theory. Okay. So now around 1.5 Kelvin, as you can see that the curve falls below the lowest measurable temperature available to us. So what we did next was around 1.72 Kelvin, you see that there is a divergence, the expected divergence that you expect in a spin-off Heisenberg chain, and this again indicates quantum criticality, right? And for fields above HS, empty plateaus because the ground state has now changed to a fully polarized state. Okay, right. So therefore, because in our squid magnetometer we could only go to around 0.38 Kelvin, what we did was for the field dependence susceptibility experiment, we send our crystals to Tallahassee, and they did this experiment of susceptibility as a function of field for different values of temperatures. So what you can see is that at very low temperature of 30 millikelvin, there is once again the expected peak, which keeps on shifting to lower fields as I keep increasing the value of temperature. Okay, so this once again is an indicator of crossover from Tomonaga-Luttinger liquid to fully polarized state, and the solid line in each are once again the quantum transfer matrix calculation done with only one parameter J by Kb of 1.23 Kelvin. And as you can see, this is a very good match between theory and experiment. Yeah, these points I have already made. So next what we did was we did a specific heat measurement as a function of temperature. The black curve that you see is the specific heat data, the entire specific heat data. And what we had to do then was to subtract the phonons from here. This was done using a combination of Debye and Einstein term. So what we found for our measurement is that you need only one Debye term and two Einstein terms. Using that, we were able to fit the experimental data, and the red curve that you see here is the specific heat curve obtained after subtracting the phononic background. Okay, these are the values of the parameters after the fit. So after I have subtracted the phonons, this is how the specific heat looks like, as indicated by Klumper and everybody. What you have is a low temperature peak here. As I keep increasing the value of field, the peak starts to go down. As before, the solid line once again are quantum transform matrix calculation for these. Once again, we have very good fit of data with theory, and all the other parameters, namely the saturation temperature, the peak temperature, sorry, etc. All of them match with what is predicted from theory. Right. Okay, there is some. Right. What I wanted to also point to you is that in all these specific heat curves as a function of temperature, you see that all these curves are linear in low temperature. This is once again indication of spinonic fermionic excitations, and at values of fields 1.72 Tesla, which is greater than the saturation field, what you have is an exponential drop in specific heat, indicating the transformation to the fully polarized state. So this is a plot of specific heat as a function of field, and you can see that there are these two peaks at HS1 and HS2. The HS1 peak is denoting the transformation of a Luttinger liquid to quantum critical state, while the HS2 denotes the transformation from the quantum critical to the fully polarized state. And so in this quantum critical state, one expects the quantum mechanical fluctuations and thermal fluctuations to be at equal footing. Okay, right. So then what we did was, because it's a one-dimensional system, field theory calculations was easy for my collaborators. So what they did is they wrote a spinless fermionic description for the Tomonaga-Luttinger liquid in this fashion. The first term is the fully polarized state, and the deviation from that because of the application of the field here, and the other higher order terms indicate criticality. Okay, so this is the ground state of the field polarized state, and this is the asymptotic scaling behavior close to the quantum critical point. So similarly, the magnetization was also derived in this fashion. So this is the saturation magnetization differing from the value of magnetization obtained experimentally through this scaling function here. And what we did was, then we scaled the magnetization with respect to the applied field and plotted it as a function of temperature. So these are the three fields at which this scaling was done, and you find that the value of the scaling parameter was found to be 0.5 for 1.72 Tesla. So this the value of saturation field was obtained by doing this scaling analysis, right? And similar calculation was also done for specific heat, because specific heat was also found to go in this scaling behavior. This is how the specific heat as a function of temperature looks like, and the fit again is giving us a value of exponent which is 0.5. Okay. So to finally confirm the scaling, we were able to find a data collapse at the saturation field quantum critical point. This is a plot of magnetization normalized with t raised to half, and this is plotted with respect to the saturation field differing from the applied magnetic field for different values of fields, and you can see that there is a very, very good data collapse as is expected if there is scaling around a critical point. And a similar data collapse was also obtained for specific heat, which was normalized with respect to t raised to half, also plotted with respect to h differing from hs normalized with temperature. Okay. So then after this, we were able to calculate the spin-on velocity. Once we figured out that our system is a very good realization of Tomonaga-Luttinger liquid, we were able to use this expression from GMRG, and if you do a low temperature linear fit to specific heat, from the slope, you are able to estimate the value of the spin-on velocity u. And it was found that the spin-on velocity u decreases with field in this fashion. And this is expected because as you keep increasing the value of applied field, the spins are getting polarized in the direction of field, and what is generated are these string-like domains of polarized spins. And the Luttinger parameter we were able to calculate using the expression between the susceptibility and k by u. So once we were able to get the value of u from the specific heat, we used that to figure out the value of k from the chi prime h data, which was measured at the same values of temperatures and fields. And this is a plot of k as a function of h. So what you find is that the values of k is positive but less than 1 for all the values of applied field. So this indicates that the interaction in this Tomonaga-Luttinger liquid is of a repulsive kind. Okay. And the other thing is that the value of k at 0 Tesla was actually 0.55, which is very, very close to the expected value of 0.5, which comes from the field theory calculations. So finally, we were able to draw the phase diagram by collating all the data that we obtained from magnetization, specific heat, and susceptibility. What you find is that these blue circles, this denotes the peak of specific heat. Similarly, so what you find is that the contour, first of all, is obtained from the Wilson's ratio. So once you have obtained the susceptibility and specific heat, you can derive the Wilson's ratio from that. And this is what we did. This is the plot of the phase diagram using the Wilson's ratio. The values of the Wilson's ratio are mentioned on the top. So you can see that in the fully polarized state, the Wilson's ratio is very, very small. In the Tomonaga-Luttinger liquid state, the Wilson's ratio carries the value between 2 and around 3.5 or so. And in the quantum critical region, just like predicted by theory, the Wilson's ratio is actually very, very large, of the order of 8. So as I said, the Wilson's ratio, the phase diagram was made using this expression for Wilson's ratio. We have been able to mark these 3 phases. Also, these dotted lines that you see are actually fits to the expression that I had shown you in the initial slide. So this is T spin-on, which goes linearly with field in this fashion, like this. And similarly, the other one is T magnon, which again goes linearly with field, like that. And in contrast to what was shown in copper pyrazidine nitrate, what we find is that the quantum critical phase boundary extends to a very, very large portion of the phase diagram. You see that from HS to approximately a value which is very, very close to 0, you find this linearity, huge amount of linearity. And okay, this denotes transformation from Z equal to 1 to Z equal to 2. I have not described this, but that's okay. And the right quantum critical line, as I said, denotes transformation of field-induced gap delta. So if now you compare this experimentally obtained phase diagram with what was predicted by he et al. In 2017, you see that there is a very nice match between what we have been able to obtain and what was calculated by he et al. Also, the other thing is that if you have a look at this phase diagram, you see that it's of a uniform color, in the sense that the value of Wilson's ratio is approximately, around 2.5 or so in this region. But on the other side, what we get experimentally is that this Tomonaga-Luttinger liquid phase seems to be bifurcated in 2 small parts with a different value of RW for these values of temperatures and field compared to this. And we have some inkling on the reason why that must be happening. So as I said, in contrast with what was predicted by theory, we have this 2 phases which was not predicted by theory. Large values of RW in the quantum critical region, exactly like what is predicted by he et al. And as you can see that Wilson's ratio seems to be a much better marker of quantum criticality. then either magnetization or specific heat. So we've made a phase diagram also with magnetization and specific heat, and you can see that Wilson's ratio does the job much better than either of them. Okay, so this paper has been submitted, it is under review, and I would like to conclude by saying that we have found a new metal organic coordination system CUD, which seems to be a very good realization of a spin-off Heisenberg chain. Quantum transfer matrix and Bethe ansatz fit the experimental data very well. Field theoretic spinless fermion description also is found to fit very well in CUD. We find very good scaling and data collapse in the regions close to the saturation field. We've been able to calculate the spin-on velocity and Luttinger parameter for the first time in any spin-off Heisenberg chain. We have been able to calculate the phase diagram using Wilson's ratio and find that the phase diagram extends to a very large portions. We have done it, and we want to estimate whether there is actually lack of ordering to ultra low temperatures by muon relaxation experiments. And these experiments have also given us some hints on the difference of the Wilson's ratio in the lower part of the phase diagram. And we are also doing inelastic neutron scattering to confirm spin-on excitations in this. And we also want to calculate multi-particle entanglement in the form of quantum Fisher information in CUD. So this is my PhD student who has done this work. This is my group. These are my collaborators. And I want to acknowledge the Department of Science and Technology, SCRB, and High Magnetic Field in Tallahassee for this experiment. And yeah, thank you very much for your attention. This is a drone picture of Isaac Trivandrum from top.
Thanks for a very nice talk. So we have time for questions. Actually, I should really encourage the students and postdocs to speak up and ask questions. I think, yeah. Oh, sorry.
I had a very naive question. So you showed that you fit your specific heat data to the dBi plus Einstein, where you had two frequencies for the Einstein model. So I just wanted to know whether those two frequencies in the Einstein model had any physical thing. I mean, can you relate
so if you actually, if you do a FTIR experiments, you are able to get those frequency experimentally also.
Okay, so like
they will
what phonon frequencies are they, the lowest ones, or I mean that's what I meant by.
I think around the middle, not the very high ones and not the very low ones, somewhere around the middle. Around.
Like why do those get? Why do you need to? Why
do they get excited?
Yeah, why is it those specific ones? That's more the.
Okay. Why are those specific ones getting excited?
Yeah. Okay.
Maybe, I mean, I don't know. So you have the material is made of copper and all these organic linkers. So the oxalate, okay, that is answer. The oxalate and the pyridine rings, the vibrations, they are going to couple to the vibrations of the organic linkers in the one-dimensional chain. And these get excited at those temperatures. So they must. Right, so multi-particle entanglement, as you know, is an entanglement between spins which are separated, let's say, far apart, but they are still entangled with respect to each other, namely that if you move a spin here, it has an effect on the spin which is at some distance away from the correlation length. So now what happens is that out of many possible ways in which you can figure out multiple entanglement in a system, quantum Fisher information is supposed to be a witness of multi-particle entanglement. And what was shown by some theoretician is that if you have multi-particle entanglement, then through quantum Fisher information, what you can do is if you do an integral of these dynamic susceptibilities with some function which is tan hyperbolic omega t by something, by doing an inelastic neutron scattering experiment or an NMR experiment and doing an integral over the tan hyperbolic function, you can estimate, or you can get a estimate of a m particle entanglement, namely that if one particle is here and the other one is here and the third one is somewhere there, m such particles, if they are entangled with respect to each other, you can get a idea of that using the quantum Fisher information. And experimentally, we actually showed it experimentally by inelastic neutron scattering on a spin-off Heisenberg chain, and we find that actually that entanglement temperature defines the limit of criticality. Instead of you assuming that at some temperature where the exchange coupling constant has been reached, you would assume that above that it will be classical fluctuations. But what is found is that instead of that, you have entanglement temperature, and which is actually larger than the exchange coupling constant. So,
am I audible?
the realization of a spin-off Heisenberg chain, yes.
Yeah, so I was wondering, how did you come up with that CUT? Seems like very complex structure. So you did some trial and error method, or was there some theory prediction that this can be realized in this class of
Right.
materials?
So yeah, what we were doing was there was a starting material that I had. I mean, not here, but in my postdoc, I was working on a material which was similar to this, in the sense that, see, look, finally it is crystal engineering. What you have to do is, there are these metal centers, in this case it is copper, then they are mediated by some organic ligand. In that sense, it is nice to work with organic materials because you can tune these organic ligands very easily compared to an inorganic one. So what we had was already a material which had copper centers, and then there were these organic linkers which were mediating the exchange coupling constant between these two copper atoms, and then some other kind of organic ligands which were trying to separate these chains. So what you try to do is work around with these organic ligands. Instead of 4-aminopyridine, try 2-aminopyridine, because you know that it has some interaction strength. So if you are able to bring these copper atoms closer in one dimension, but you are able to bring them away from each other in the second and third dimension, then structurally you would assume that what you got is a one-dimensional material. And of course, the interaction between those two copper should also be antiferromagnetic kind. So you should have done susceptibility and calculated Curie temperature and figured out that that must be the case, and then from that you can work on and tune these things. And of course, people like Shobna can give us ideas with the DFT and try these materials and so on and so forth.
So currently there is no such a theory prediction that you can try with this kind of material, other than CUT, obviously.
I am not aware. I am not aware, but maybe people who do calculations can say. I think there are large number of calculations, in the sense that people try to modulate the interactions between metal centers by these crystal engineering, as they called. I mean, we do it directly in the lab by trying out reaction times and dwell times and changing ligands, but I think also from theory.
I was not going to.
Okay. Yeah.
Actually, can I ask one question?
Yeah.
So are DM interactions important, or this is like inversion symmetric and there is no, I'm just wondering.
No, in this, there is.
Yes. And you mentioned that
actually,
you had some.
in some organic materials, I think strontium cuprate and all, where people had initially thought that they were 1D chains and stuff was happening, then there were DM interactions in them, and various observations were then actually explained by those, but in this case, no.
Maybe one last question and then.
So the schematic that you have shown for a antiferromagnetic chain, Heisenberg antiferromagnetic chain, it looked like a spiral kind of thing. So I mean, is there any
Spiral?
Yeah, in the slide number 6, I think you have shown.
Yeah, so what we are trying to, because you see the Heisenberg spin is on a sphere, right? So it's not just up, down, up, down. So they are antiferromagnetically aligned, but one is like this, other is like this. The third one will be like that, fourth like that, something like that. So in spiral is not spiral of, how to say, it's the rotational of the spins on the Heisenberg, on the sphere. There's a psi dot Sj, so it goes like this on the sphere. I mean, it is three-dimensional. The spin space is three-dimensional, but the lattice space is one-dimensional. So the atoms are on one dimension, but the spins are free to rotate on a sphere.
All right, so let's thank Deepshikha. And I had a